Okay, this first lesson will be an overview of what probability means, and then a discussion of some terminology and notation so we know common ways to write things and refer to things that we need to know about probability. So to talk about what probability is, let's consider this situation. On your drive to work, you encounter one signal light. When you arrive at the signal, sometimes it's red and you have to stop, and sometimes it's green or yellow and you can go. Because you don't leave at a specific time each day, the exact time you arrive at the signal would be random. But there is an underlying structure in the situation. Let's say that the signal light is red for 2 minutes out of every 10 minutes, and then it's green or yellow for the rest of the time. Then that means for 20% of your arrival times at the signal will be red. On any particular arrival time, anything can occur. Right? You could encounter the red light or you can encounter the green or yellow light. But if you were to keep track of the signal at your arrival time over many days, then eventually you'll start to see this underlying structure emerge, that about 20% of the outcomes will be red and the rest of them will be green or yellow. Here's another example. Let's say we flip a fair coin, fair meaning that it lands on heads 50% of the time and tails 50% of the time. It could land with heads up or tails up. So if we flip it 10 times, we might see this outcome: heads, then tails, tails, heads, heads, tails, heads, tails, heads, tails, in that order. Or we could see this outcome: tails, heads, heads, tails, heads, heads, tails, 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 tails. Or what about this possibility? All 10 of them would be heads. Yes, this is definitely possible. Even though it seems unusual, it's really not that unusual. It's just one of the many possible examples of things we can get if we have 10 flips. Each flip is completely separate from the last flip, so every time you flip the coin, it has the same chance of landing on heads, 50%. Is it likely to happen that we would get 10 heads in a row? Not particularly, but it's just as likely as getting this pattern: heads, tails, tails, heads, heads, tails, heads, tails, heads, tails. It's true that we should expect to see heads about 50% of the time, but only if we flip the coin many times, and 10 times is not enough for us to be able to say that it's going to definitely look like what we expect, 50%, the theoretical probability. So let's define some terms. What should we call this percentage of desired cases that we observe in our experiment with a small number of trials? There's a couple of different terms that people use for this. One of them is observed relative frequency. Complicated sounding. Frequency is just another word for count, and relative means that this count is being compared to or is relative to the total observed observations. And then we could use the term experimental probability or empirical probability. We can call it the probability or likelihood that this event, say 10 heads occurring, would happen just based upon our experiment. So what do we call the structure of underlying structure of the percentage of desired cases that's built into the structure? The 20% of the times of arrivals being red lights, or the 50% of heads of flips being heads for a fair coin. That's usually called theoretical probability, or more commonly we just use the word probability. So when we use the word probability, we're going to be talking about this theoretical underlying structure probability, not the probability that we would see in a small number of cases. So this whole idea can be referred to as the law of large numbers. The law of large numbers says that the observed relative frequency of red lights will approach the probability that the light is red, which would be 20%, if we observe for many days. The law of large numbers says that the observed relative frequency of heads will approach the probability of heads, which is 50%, if we flip a fair coin many times. So how many times do we have to observe something before the law of large numbers kicks in and we expect to see the percentage being close to the actual probability? Well, there isn't really an absolute answer to this. The idea is that as the number of trials goes up, it gets less and less likely that we'll observe something that's very different from the expected probability. When that likelihood is small enough, when we've observed enough trials, then we can say that we expect the probability of the theoretical probability to be observed. If you want a rough number, personally I picture something like somewhere between 25 and 100 trials is high enough for most situations to be able to say that we should be seeing the theoretical probability. Okay, mostly though we're going to compute the theoretical probability, and we'll just call it probability. Just important to keep in mind that if you have a fairly small number of observations, say certainly anything below 25, anything at all could happen, even things that are very different from what the probability predicts. Okay, the rest of this video we're going to define some probability terms and notations. So many probability problems involve in counting things in various ways, and one way to count things is to group them into collections that we call sets. So a set is defined as a collection of objects that we wish to treat as a whole. Sets are usually identified by a capital letter, and there's different ways to indicate what's in a set, but in probability we usually use what's called the roster method, which shows the complete list of sets, the items in the set, which are called elements, surrounded by curly braces. So something like this, right? This is a set that's being listed in roster notation. The set D consists of the numbers 3, 5, 7, 9, 11, 13, and 15. So that's called the roster method of listing sets. There is another way to show what's contained in a set. It's called set builder notation, and you're more likely to see this in more advanced math classes. Instead of listing all of the elements in a set, it'll provide a rule, something like this. This is read D is the set of all x such that, this line is read as such that x is an odd integer between 3 and 15 inclusive. So that actually gives us the same set as was on the previous page. It's just the set of all the odd integers between 3 and 15. The reason we sometimes use set builder notations is if we have large sets, then sometimes it would just take too much writing to write out all of the elements in a set. Okay, another very convenient way to represent sets and their interactions, which we'll use frequently in these videos, is called a Venn diagram. The box is called U for universal set. That's all things that are under consideration in the problem. And then a particular subset, A, is a group with only some of the things in U, usually represented by circles, although they can be any shapes that designate a portion of the universe. Okay, the complement is the set of all the things that are not in the set we're identifying. So if we're trying to find the complement of A would be everything in the white circle, and the complement of A would be everything else in the universe that's outside of the white circle. So that can be written different ways. I like to write it with a bar over the top of it, A bar. Sometimes we write it with a little quotation mark that's read A prime, and sometimes some books put A and a capital C for complement up there in the exponent position. But all those things mean not A, everything not in A. Okay, what if we have two subsets, subset A and subset B? Well, we can talk about the union of the two subsets. That means anything that's in A or in B or in both. The union, if you were to unite the stuff in both the sets. So in set builder notation it would be A union B it's a set of X such that X is in A or X is in B. That can also be read A union B. You can say those elements in A or B, or those elements in A and B combined. All different wordings that mean this thing called the union. So something can be in the union if it's in A or B. So this symbol right here, this U-shaped symbol, is the logic symbol and the probability symbol that means or, and we'll frequently use that symbol to mean or. Okay, sort of the opposite of the union is the intersection. If you talk about something needing to be in A and B, so to be only in the intersected area, this green area, that's called the intersection. So you can read that as A intersect B, those elements in A and B, those elements in common to both A and B. Something can be in the intersection only if it's in A and B, so that symbol, we have to have a different symbol, and it's that union symbol but flipped upside down. That symbol right there means intersection, and we'll also use it to mean and, because something has to be in A and B for it to be considered in the intersection. So that's our general symbol and probability for and. Okay, some words. The word trial, we'll use that to mean one complete occurrence of a situation. Sometimes some books call this an experiment or an observation. An example of a trial would be a single roll of a die, or tossing a coin twice. Even though we toss the coin twice, the experiment might be about what happens when we toss a coin twice, so doing both tosses is considered one trial. An outcome is one possible result that can occur when a trial is conducted. So for example, if the trial is a single roll of a die, an outcome would be getting a 5. Tossing a coin twice, the outcome would be tails, then heads. Sample space. A sample space is a set of all possible outcomes that can occur as a result of a trial. So for example, if we're rolling a single 6-sided die, the sample space, which we usually use the capital letter S to represent, the sample space would be the set of the numbers 1, 2, 3, 4, 5, and 6. If we're talking about tossing a coin twice, as a trial, then the sample space would be, we could get heads then heads, heads then tails, tails then heads, or tails then tails. So it's just a listing of all the possible outcomes that can occur. Okay, an event is any subset of the sample space. So sometimes events are referred to as the desired outcome or set of outcomes that we're looking for the probability. So an event, for example, would be, if we're rolling a six-sided die, we could define an event to be, say, rolling an even number, if we're trying to find the probability of getting an even number. So we define what's called the event space. Usually we use the capital letter E for that, and we just list the portions of the sample space which are included in the event. In this case, it would be 2, 4, and 6, because those are the only outcomes which are even. Maybe we have a trial consisting of rolling or flipping a fair coin twice, and so we wanted to find the probability of obtaining at least one tail. So the events which, the outcomes which include at least one tail would be heads tails, tails heads, and tails tails. So those three events would be in the event space. Okay, so the probability of an event, that's just a numerical value between 0 and 1, which represents the likelihood, how likely the event is to occur. It's written with a capital B, almost like an algebraic function, the probability of, and then in function notation, inside the parentheses, we include what is the event that we're finding the probability for. So probability of an event has to be between 0 and 1. Probability of 0 means the event is impossible. A probability of 1 means the event is absolutely certain. But usually probabilities are numbers between 0 and 1, and we can write that as either decimals, fractions, or percentages. So let's say we have a coin that's fair, and we want to know the probability of getting a head, and we know that's 50%. So that can be written as the fraction. We would say the probability of head is 1/2, or we can write it as a decimal. The probability of head is 0.5, or we can write it this way as a percentage. Probability of head is 50%. But if you're going to write percentage, you have to include the percent sign. Okay, so three ways to write it: fractions, decimals, and percentages. A probability model is a listing of all the outcomes in the sample space along with the probability of each outcome. So let's say we wanted to create a probability model for rolling a fair six-sided die. The sample space is 1, 2, 3, 4, 5, 6. So in a probability model, we usually do kind of like a horizontal T-chart like this. And on the top, we'll list all the outcomes. The outcomes are 1, 2, 3, 4, 5, and 6. And then below that, we'll list the corresponding probabilities. The probability of getting a 1, the probability of getting a 2, and 3, and 4, and 5, and 6. I'm not going to write those now because that's what we're going to cover in the next video, is how to find these probabilities. But one thing that's true is if you sum up all the probabilities of all the outcomes, they always must add up to 1. And that's because it's absolutely certain that if you conduct a trial, one of the outcomes will occur. Okay, that should be it in terms of major terms and ways of writing things that we'll encounter as we study probability. So if you need help with just one probability topic, at this point you can proceed to that topic's lesson directly or just watch the examples. Or if you want a really good overview of all of high school and early college probability, you could watch all the lessons in sequence. Thanks for joining me for these videos. I really look forward to sharing with you this interesting area of mathematics.